So welcome back, everyone. So let's start the second talk, be given by Sebastian Mizera from the IIS. He'll tell us about tropical realization of the Wilsonian paradigm.
All right,
Please.
awesome. Thank you so much for the introduction, and thanks to all the organizers for setting up this meeting. It's really a pleasure to be here. So today I will be talking about work in progress together with Nima Arkani Ahmed from the IIS, as well as Aaron Hillman, who's a grad student at Princeton University. So before I start properly, let me thank even more the specific organizer whose idea it was to include the word beyond in the title of this workshop. So I think as we've seen yesterday, and we'll see even more later in the week, there's been a lot of progress in the sort of percolation of the set of ideas that used to be applied to toy model theories D-log forms that nowadays sort of get applied more and more to realistic physics. And I think it's a great direction. So although today I will not be talking about positive geometries per se, I will certainly be talking about the set of ideas that has been influenced a lot by the positive way of thinking about scattering amplitudes. So more specifically today, I wanted to focus on the tropical geometry. So just as a part of the motivation, I'm going to, on purpose, not explain what tropical geometry is. Let's just stick with the intuitive picture. And let me review quickly the way that it actually appears in scattering amplitudes. Okay, so there are basically two versions in which it has so far appeared. First one is the scattering on the wall sheets, such as in string theory. So what you can consider is a moduli space of Riemann surfaces at a given genus. Then you can consider tropicalization of that moduli space. And at least intuitively, we know that that lands us on the sort of Feynman diagram-like degenerations of the Riemann surface. So it's really, in this case, the tropical geometry is a realization of the idea of OPs, or the fact that punctures can collide, or we can shrink some geodesics on the wall sheets. And it gives us this picture of sort of left-right factorization as pioneered by this work of Turkin many years ago. And more recently, we've seen an outpour of new papers by various authors on related topics, genus zero, and applications also to different types of configuration spaces. And we've seen also plenty of talks last week. Okay, let me contrast this idea with the case of the world lines. So instead of world sheets, which are two-dimensional objects, what you can consider are world lines. And in this case, what will happen is that applying the ideas of tropicalization to this case is going to lead us on the sort of natural Wilsonian notion of embedding subgraphs, for example, this subgraph within this one, this one, and this sort of intuitive idea of separation of scales. So there's been also recently, there's been a few works independently by Schultka, by Panzer, as well as Borensky, so which go into the same direction. And hopefully today I will present a different perspective on the set on a similar kind of set of ideas. So let me make the contrast between world sheets and world lines even more clear straight away. So I think it's the clearest to see it from analyzing what happens when punctures start degenerating into each other. So on the world sheet, what we have is violin invariance, and essentially because of violin invariance, the positions of punctures are dimensionless quantities. Okay, so they're just some numbers. And then what happens as they collide, the degeneration is captured by the Green's function. Okay, and locally, as these punctures collide, the Green's function behaves as a log of Zi minus Zj on a two-dimensional surface. Okay, so there's nothing fancy going on here. Then when you consider world lines as opposed to world sheets, what you have is positions of the vertex operators are described by this, roughly speaking, the proper time along this world line. Okay, so now because we're in one dimension, instead of a log, we get a linear behavior as things start colliding. And here's the crucial difference between worldsheets and the world lines is that now associated to this degeneration, we have some mass scale. And essentially that mass scale is what gives rise to this picture in which we have different scales fitting together into a big factorization, which now instead of sort of left-right factorization is in and out in terms of the separation of scales. And this gives rise to the central idea that motivates this talk is that tropical geometry will be a realization of the idea of the separation of scales in physics. So this notion goes both ways. So if you're a physicist who might never have heard about tropical geometry, or maybe you are always confused about where it comes from, well, in a sense, you already know about all the ideas. Maybe you haven't connected them before, because by the end of this talk, I will try to convince you that it's exactly the same idea as the Wilsonian separation of scales. And likewise, if you're a mathematician who might have know everything about tropical geometry, hopefully by the end of this talk, you will also learn some new physics. Okay, so we've been working on this for quite a while, and it grew out into a very multifaceted story that encompasses many directions, including randomization, soft collinear physics, Landau analysis, wordline formalism, and related ideas. Obviously, I will not be able to explain all that in a single talk, but let me just give you a quick overview. The overview is that we are able to study two kinds of degenerations, which are separate in a sense. One are the threshold singularities. So these are the peaks that you see at the particle colliders. And this is some work that we're doing together with Simon Tellen from Max Planck at Leipzig, in which we study this kind of Landau analysis applied to this tropical geometry formalism. On the other hand, what you can consider is complementary to thresholds. We also have UV and infrared factorization. And this is actually what I will be focusing on in this talk. So that's work in collaboration with Nima and Aaron. Even more so, what I wanted to do today is not explain this fully. I will just focus on two very simple examples. And I think once you understand how these ideas fit into these two examples, basically you will know 90% of the stuff, and the generalization to arbitrary other diagram will become clear. Okay, so the plan is very simple. What we're going to do is first we're going to review the Schwinger parametrization. Then we're going to study UV divergence on the simple example of a sunset diagram. And then we'll move on to infrared divergence on the simple example of a single box. Okay, so unless there are any other questions, any questions about the setup, let me move on to the first point. Okay, so Feynman integrals in the wordline formalism give us these kind of integrals. Okay, so first of all, we have a set of Schwinger parameters, which I will call alpha sub E. So E is an internal edge, and it ranges from 1 through capital E, where capital E is the total number of internal edges in our diagram. Okay, so this gives us this factor here. Then in the rest of the integrand, we can have some numerator. So the numerator encodes all the interesting vertices, all the interesting physics of interactions. And in the denominator, we have two other polynomials, U and F. These are the semantic polynomials, which are polynomials in the Schwinger parameters. Okay, here everything is raised to a power gamma, where gamma is the degree of divergence of a given diagram, which is equal to the number of edges, internal edges, minus a half number of loops, dimension, plus the degree of our numerator. Okay, it also gives us this funny gamma prefactor. And finally, because of the descending from the reparametrization invariant on the invariance on the word line, we have to mod out by an overall scale within this integral, which gives us this projective measure on the E-1 dimensional projective space. Okay, so that's this measure. And this measure is essentially responsible for the overall GL1 scaling. So we can rescale all the Schwinger parameters with some constant number lambda. So this is just the overall dilation of the diagram of all the edges at the same time. And we'll fix this redundancy, this degree of freedom, by simply setting one of the Schwinger parameters, say the last one, to 1. Okay, so in this setup, the projective measure can be written simply as an integration of the remaining e-1 Schwinger parameters from 0 to infinity each. Okay, then in the rest of the integrand, we need to understand what the semantic polynomials u and f are. So if you have not seen this, don't worry, because I'm going to give you examples later on. This is just to flash, to remind those of you who have seen it, that u is the one defined as a sum over spanning trees, and f is defined as a sum over spanning 2 trees with some coefficients and corrections from the internal masses me. Okay. So such integrals don't converge essentially for 2 separate reasons. And the first one is are the threshold singularities that need to be, or the branch cuts that need to be regulated, and these need the Feynman I epsilon prescription. So the way that you can implement it on the word line is that instead of integrating over the original Schwinger parameter along the real axis, what you need to do is give it a small phase to rotate it into small imaginary directions. Okay, so this phase turns out to be proportional to these derivatives. The way to implement it correctly is for it to be proportional to these derivatives of the semantic polynomial. And you can show that this choice of shifting the Schwinger parameters is the one that implements the correct causality conditions, precisely unless all these phases vanish. Okay, when all phases vanish, these equations are known as the Landau equations, and this is what signals a singularity. So that would be a starting point for the other branch of this tropical geometry that I'm not going to talk about today. And today I will assume that these are not satisfied, so we're computing some well-defined Feynman integral. Okay, on the other hand, on top of the Feynman I epsilon, we also need to regulate the UV and IR divergences. And in this talk, we'll just do the dumbest thing possible. We're just going to employ DIMREG, the dimensional regularization, which tells us that what we're supposed to consider is, instead of doing 4 dimensions, we're going to compute our integral in 4 minus 2 epsilon dimensions, where epsilon is some complex parameter. Okay, so just to make sure everyone is on the same page, let me emphasize that schematically UV physics corresponds to the configurations in which Schwinger parameters, which measure the lengths of each part of the word line, when they shrink to 0, this is what we would call a UV singularity. And on the other hand, when the word line becomes very, very long, this corresponds to infrared singularity. Awesome. So now we can move on to an explicit example. Okay, so this example will be this sunset diagram here with a single Mandelstam, depending on the single Mandelstam invariant S, and with 3 possible masses. Okay, so here the number of internal edges is 3, number of loops is 2, and the dimension is 4 minus 2 epsilon. Then the U semantic everything will depend on these 2 semantic polynomials. The first one is just given by alpha1 times alpha2 plus all permutations. And then the F semantic polynomial is the Mandelstam invariant S times this combination minus the corrections from the masses times the U that is defined here. Great. So now the Feynman integral, after you just plug in into the definition of the Feynman integral, looks like this. Okay, so we integrate over alpha1 and alpha2. We have the semantic polynomials defined here, raised to some powers that you can compute, and everything is regulated with this epsilon factor. Okay, so now what you can do is you can look at this integrand and you can naively try to look for divergences. We know intuitively in physics that there are supposed to be some bubble divergences associated to this. So the way that you will look at it is, well, we integrate everyone from 0 to infinity. So we have this positive quadrant, and you see that there's some singularities that you can approach when one of the Schwinger parameters goes to 0 and the other one goes to 0. However, you have to be much more careful when you consider what happens when they both go to 0 simultaneously. And the reason for that is that everything depended on, like this integrand here had the U and F semantic polynomials. And as you can tell, they vanish at the origin. And this means that they pass through the origin in some way. Okay, and that single point, or of that point, is in fact the part of the integrand that dominates everyone because it has all the information about the divergences. And the point here is that that information is not directly accessible because we have this exceptional divisor that you need to blow up into to zoom in on the specific degenerations. So the standard approach is that of the iterated blow up of all the boundaries. And in the Feynman integral literature, this is known as the sector decomposition that has been employed for many, many years. And more recently, there's been a diagrammatic version of that, more based on algebraic geometry, in the work of Bloch, Esno, Kramer, and later systematized or generalized in this full generality by Brown, in which you can diagrammatically do this blow up in the correct orders and all that. However, this is not what we're going to do in this talk. This is the standard approach. In this talk, what we'll do instead is employ so-called tropical compactification. And the magic of tropical geometry is it will give us all this information entirely for free. Okay, so we'll not have to do anything. We'll just follow a simple procedure, and we'll see that all the divergences will be clear-cut. In fact, I use this fancy word, it's tropical compactification, but the purpose of this talk is that what we want to do is simply discover the way that the way a mathematician would talk about it by just following a couple of simple steps. Okay, so let's discover these tropical rules. So the first step is going to be pushing all the divergences to infinity. This is a fancy way of saying that we do this change of variables, okay, where the Schwinger parameter is going to be written as an exponential of some tau. And in those tau variables, all the divergent information about the amplitude is pushed to infinity. Okay, so the UV singularity, the one where the edge shrinks, is at minus infinity, and the infrared is at plus infinity. However, you have to be slightly careful about the interpretation, and that's something that will come back in a second, in that you remember that there was this overall GL1 redundancy. So you can equivalently think about a set of edges going to UV singularity or the complementary set going to infrared. Okay. So as a first step, let's just plot the log of the integrand that we've just defined here. Okay, we have some function here. Let's just plot it and see how it looks like. Okay, so we're going to plot it. The only independent variables are tau1 and tau2. And this is how it looks like. So you can identify in this diagram, roughly speaking, we have the whole two-dimensional plane, and we have the UV in this direction, infrared in this direction, and likewise in tau2. However, this diagram is not highly illuminating. It's in fact very difficult to read because we see that it decreases in this direction and increases in this direction, but not everything is clear. And it's not clear because it's difficult to read off, in fact, the rates at which the divergence happens at infinity. Okay, so the next step is going to be factoring out the overall log divergence. What I mean by this is that I'm going to take my integrand here, and I'm just going to multiply it by 1. Okay, multiply it, divided by this product, and multiply it back in. So in this way, we factored out this prefactor, which factors out the information that F1 decays logarithmically at infinity. And then what we can do is look at plotting this specific function here. Okay, so schematically, the expectation is that once we've modded out by this overall marginal divergence, you can plot the integrand and look at what happens at infinity. If your integrand goes to a constant at infinity, this means that there is, in that direction, there's a marginal divergence. So there's a log divergence in this direction. because it comes from the prefactor. Similarly, if your integrand is going to grow in these variables, it will signal the quadratic or higher divergence of the Feynman integral. And finally, if it decays, it means that everything is convergent in that specific direction. So what we can do is we can just go on and plot this. Okay, so once we plot this, we find this picture here. So as you can tell, we have tau1 and tau2 variables, and we have these constant level surfaces. So there are some directions, these blue regions, where the integral decays very well. But then there are also some free distinguished directions here, here, and here, in which the integrand goes to a constant. So this is exactly what we wanted, because it signals the log divergence of the integrand. If you're a mathematician, you would call these kind of diagrams amoebas. That's the technical term. So let's look at one of these directions and what it tells us about the physics. Okay, so the natural direction to look at is here. Okay, so this is the direction in which both tau1 and tau2 go to -infinity at the same rate. Okay, they go along this diagonal. And if you translate it into Schrödinger parameters, it means that it's precisely a configuration in which we have our Feynman integral here, and the edges 1 and 2 went to 0. So that's a pinch of this sub diagram of this bubble, and it's just provided to us by this by plotting this integrand. Similarly, we can look at this direction. This is slightly more tricky because tau1 goes to infinity, but remember that tau1 going to infinity is equivalent to the complement tau2 and 3 going to -infinity. So in fact, that diagram is precisely the same as the one that we've seen here, just with permitted labels. Okay, so this is the direction in which tau2 and 3 shrink to a point. So that's a bubble subdivergence for this subdiagram. And likewise, by just permitting labels, this specific direction is a UV divergence associated to shrinking of this subdiagram. Okay, do we have any questions about this? Hopefully it's very simple. Great. So now what we can notice is that the divergences are really associated to an enhanced symmetry in certain directions. Far away, just somewhere here, you see. Wow, sorry. I think I cut out. So let me repeat that. So the divergences are associated to enhanced symmetry in certain directions. Okay, so we can see it, for example, in here, that as you go in this direction, when the two Schrödinger parameters start shrinking at the same rate, our integrand acquired a new symmetry, okay, which you can see here that these level surfaces become constant. So there's some symmetry here. And likewise, if you go in this direction, there's a symmetry here and this symmetry here for the other bubble. Okay, so let us make this more intuitive, more precise algebraically. So we can, for example, look at this diagonal direction in which the Schrödinger parameters alpha1 and alpha2 became very, very small, and in fact they would be subleading to the remaining Schrödinger parameter alpha3. Okay, so once you apply this to the U semantic polynomial, it was given by these three terms, but we shrink alpha1 and alpha2. So this means that this is very, very subleading, and the leading orders are given by these two factors. Okay, so just alpha3 times the sum of alpha1 and alpha2. And similarly, you can look at the F and apply the same procedure. You just go in this direction on the plot. And what this means is that this, once again, vanishes quadratically because we have this divergence. So the leading factor is in fact just given by here times what we already have seen with U. So if you work it out, we're going to get this factor in here. Okay. So we conclude that in this specific direction in the diagram, your integrand can be approximated. So this was our original integrand, but in the specific directions, the integrand can be approximated by these functions. Okay, so once you work out this factor, it just becomes simplified to this guy, and there's some regulator as well. And as you can see, this is precisely what I meant by the additional symmetry that you acquire in specific directions, because we found an additional GL1. This GL1 is precisely can be described by shrinking both alpha 1 and alpha 2 with the same scale to 0, so some small lambda. And as you can tell, if you just rescale it here, everything is invariant. So it's a symmetry of the integrand. And this is precisely the symmetry in the tau variables that we've seen before going in this direction. Okay, so we conclude that these parts of the integration region give us this kind of integral here, where we had the original integration measure modded out by the overall scaling of the diagram, but the integrand acquired an extra symmetry in specific directions. And that's precisely the signal of the divergence, because we have some extra symmetry that we have not fixed, so that gives us an infinity. And in fact, if you included a regulator, it's going to give us something like 1/epsilon in DIMREG. So the idea is to learn precisely how to mod out by these additional symmetries. And the integral that we, roughly speaking, need to do is the original integral, but in certain directions, we have to mod out even more to extract the sort of leading coefficient of this divergence. Okay, makes sense? It almost does, but there's one catch. So there's something wrong with the logic that I mentioned above. And I was wondering if anyone from the audience has any guess as to what that breakdown of the logic might be. Okay, so everyone is shy. I'm sure there's tons of experts in the audience. I'm sure everyone knows this extremely well. But in order to say that we approximated our integral, we sort of implicitly assume that we have this regulator factor. So when we call it a regulator, we implicitly assume that epsilon is infinitesimal. But unfortunately, this is not how dimensional regularization works at all. Epsilon is not supposed to be infinitesimal. Epsilon is supposed to be really a complex variable. Okay, so what happens here is that calling this factor here a regulator was assuming epsilon is infinitesimal, but in general, what it is some complex variable. And it might well be that your integral in certain directions is not defined close to 0. It would be defined, say somewhere here. You compute that integral, that part of the integral there, and then at the end of the computation, you analytically continue everything to 0. And it might be that different parts of the integral converge in different regions, then that's what you're supposed to do at the end. So in other words, approximating the integrand does not approximate the integral if the latter doesn't converge in the first place. So that logic that I mentioned above, strictly speaking, only works for log divergences, in which you can actually show that everything is defined close to, that the approximation scheme that we used is actually valid. So if you know that your integral is going to, or we'll see how to diagnose the fact that your integral could have power log divergences. In those cases, you have to be slightly more clever, think about some ABPs and so on that we'll ignore for the purposes of this talk. So we'll study only log divergences, and certainly that has been true in the example above. Great. So now we've established that to study divergences, both UV and infrared, in this case UV, we have to look at what happens at infinity. Okay, so this means that we need to focus on this limit in which we take the exponents of our alpha to infinity. Okay, so we rescale all the taus and we look at what happens. We don't care what happens near the origin. After we do this, we can just plug in and see what happens on the example of the U polynomial. So for the U polynomial, we just plug in this definition. And as you can tell, the multiplication here became an addition in terms of taus. And so this is exact. And in the next step, what we do is we rescale delta to infinity. So this means that when we rescale delta, only the maximal of these exponents will be dominant. So this tells us that in this limit, we're going to have delta times the max condition on our taus. And these are just tropical rules. So if you've seen it before, this is exactly how the multiplication becomes addition tropically, and also how the addition becomes a max tropically. Okay, so if you've never seen tropical geometry, this is what it is about. So once we know this, what we can do is we can introduce the following function that we call trop, and it's going to mimic the fact that it's going to study the large UV and infrared behavior of our function. Okay, so our function in this example was given by this product of alphas times some combination of U and F. So the tropical version is going to be just sum of the taus, which corresponds to these factors, and then minus 3 times this U that we've just computed here, plus max of whatever comes from these monomials in the F semantic polynomial. Okay, so we've concluded that our integrand behaves like e to the trop plus subleading in its corresponding limits. And the simplification here is that, of course, the trop, as defined here, is a linear, in fact, a piecewise linear function. So that simplifies the analysis a lot. And in fact, what we can do now is we can go on and plot this trop function. And as you can tell, it looks very similar to the graph that we've seen just above. So let me scroll to it. Okay, we've seen this integral, this integrand, and we concluded we wanted to study this asymptotic limit. And asymptotically, the two plots agree. Okay, so we have some way of approximating the integrand, and as you can tell, there are some three distinguished directions here, here, and here, which correspond to, in this case, the solution of the trop function being equal to 0. Okay, so these are precisely the divergent directions. So a diagnosis of a divergence will be when the tropical function goes to 0 in certain specific directions. Okay, if you're more mathematically inclined, what you can talk about is you can talk about the normal fan of this setup. And what this normal fan tells you is that there are 6 directions. Three of those, the red ones, are the ones that correspond to actual UV divergence. And there are 3 which are more safe, this direction, and this direction, which just corresponds to shrinking a single edge where nothing dangerous happens. And then we have these 3 separate regions. As you can tell from the plot, there were regions with this enhanced symmetry in which there was a symmetry in this direction, in this chamber, here and here as well. And these are the domains of linearity of our trop functions. So these are this region, and these regions are the ones that share the same symmetry. Okay, if you like polytopes, what you can do is, of course, you can associate a dual polytope to the setup. And in this dual polytope, because we had 6 rays in our normal fan, this polytope is a hexagon, then each edge is going to be some subdiagram that you can shrink, either a bubble or a single edge, and you can describe the information in this way. So for example, for the UV bubble subdivergence that we've just studied, say this guy, what we find is you can actually do the remaining integral in this direction. The analog of modding out by this symmetry factor is doing the integral separately in the direction where we had the divergence. So splitting our integral into this direction times the rest. And this direction is precisely what gives us the 1/epsilon from infinity. And the rest gives us some coefficient, which in this case turns out to be very simple and is equal to 1. And in fact, this integral here, as you can tell, what we need to do is we have to compute the leading order of something that logarithmically is regulated with some epsilon and so on. So this is exactly the connection to volumes of dual polytopes, intersection theory, and so on, in which we have to study these limits of integrals as epsilon goes to 0. Okay, so you can compute the leading divergence of this specific diagram, and it's what you should get. Okay, so do we have any questions at this stage? If not, then I can move on to the more general story. The more general story is going to be just considering a general Feynman diagram in which we just used the definition from before, but now we've multiplied everything by this, rescaled everything by this product of Schwinger parameters, like so. And then we can introduce the trop function that is tropicalizing this part of the integrand. Okay, so the trop function is just going to have a couple of factors. There's this sum of taus, which is mimicking this. There's a max condition on all the monomials in N, which is the tropicalization of this. And then from here, we have the max over all spanning trees and max over all spanning two trees corresponding to U and F semantic polynomials respectively. Okay, so some general features are that provided that the trop function is non-positive everywhere, like so, then the integral has at most log divergences. And we've seen an example of that happening above. Okay, then there are special directions in which the trop function goes to 0, and these are precisely the directions in which the integral becomes divergent, and it also determines the precise scaling of Schwinger parameters that you're supposed to shrink or expand, which is determined by this direction. And the procedure is in fact completely general. So we've seen it on a simple example, but it works for any UV or infrared singularity, provided it's at most log, any masses, any planarity, and so on. Okay, so once you determine that, also the normal fan, which generalizes what you've seen in the examples, determines exactly how the divergences fit together in a bigger structure. And this is the connection with BPHZ, the overlapping divergences, and studying how different diagrams talk to each other when they shrink. Okay, and finally, the leading coefficient is related to positive geometries in the sense that generalizes what we've seen above, in that the leading coefficient is just determined by the 1 over epsilon to the specific power of the trop equals 0 space, of the dimension of the trop equals 0 space. And then what you have to compute in the rest of the integrand is this kind of function, which naturally splits into computing volumes of the dual polytopes times some coefficients. So you can use it as a computational tool. Okay, then a cool fact is that the dual polytope to the trop space can be defined in terms of Minkowski sums and Minkowski differences of the following Newton polytopes. Okay, so we can define a Newton polytope of the semantic polynomial U and F. Okay, so they give us some nice polytopes. And the cool fact is that they actually have known UV factorization properties. Okay, and the UV factorization properties are as follows. So as an analog of what you might be familiar, say, from string theory or moduli spaces, in which on the boundary of the integration space, things split into left and right. This is precise analog of that for Feynman integrals, in which things split into in and out, sort of this Wilsonian notion of renormalizing couplings. Okay, so the way it looks like is that we can start with some diagram G, and then let's say we have some subdiagram within it, let's call it gamma. Then the boundaries of these polytopes are going to split factor into gamma times what we call G mod gamma, which is the same diagram, but with the subdiagram gamma contracted to a point. Okay, and the specific rules that I'm not going to spell out sort of give you some restrictions on the allowed gammas and G mod gammas, depending on which polytope you actually study. Awesome. So let me also mention that the specific combination of the Minkowski sum of U and F polytopes is something that has been seen before, studied before by Schultka as a realization of this BEKB iterated blow-up procedure. So he showed that the facet structure of U plus F is sort of equivalent to the blow-up procedure that people have studied before. And this, in fact, gives you interesting connections to generalized permutohedra and other graph matroids and other interesting objects. Okay, so I mentioned that everything generalizes also to infrared. So the natural question is, can we see this on some simple example? Okay, so let me move to this example without delay. And the one that we're going to study for the purposes of this talk is the simple box diagram, which depends on the two Mandelstam invariants S and T. And I'm going to set all the internal masses to be 0. And I'm also going to include 0 mass here, 0 mass here, and 2 massive corners. Okay, so this diagram has 4 edges, 1 loop, and it's in 4 dimensions. So famously, this diagram has a soft collinear singularity associated to this corner of the diagram, which corresponds to a situation in which, if we call this leg L, the momentum of this leg, the L, then it has this soft collinear singularity in which L squared becomes 0 and it becomes collinear with the external momenta P1 and P2. Okay, so from here we see that it's known that this integral has to behave like 1 over epsilon squared in dimreg. So what we want to see is the way of understanding that from our tropical way of thinking about integrals. Okay, so the specific integral, once you write it down, it looks like this. There we go. So U is just the sum of all the Schrödinger parameters. F is the specific combination of 4 monomials in the S, T, and depending on the masses. Okay, and then if you look at the exponents, actually this part of the integral does not feature U, just the F to second power. Okay, so then once we do our GL1 fixing for the overall scale with setting alpha 4 to 1 or equivalently tau 4 to 0, our trop function is just given by this combination. Okay, so this combination just comes from the alphas and minus twice the max condition on all the monomials that appear here after using this gauge fixing condition. Okay, so this monomial becomes this factor, this monomial, this factor, and so on. So now what we can do is we can plot this trop function, and that graph is not super illuminating because it might be difficult to read off, but one thing that is clear is that we have some piecewise linear function and it decays. So when it becomes more blue, it means that it decays. So it decays in certain directions, but there's a specific direction in which that the solution of trop equals 0 exists. And remember, that's exactly what we associated to signaling and infrared divergence. Okay, so of course, plotting things gets out of hand very quickly, but of course, the point of that is that all the conditions have become very algebraic, so you can solve it at any number of Schrödinger parameters, like so. So for example, if you just plug it into Mathematica and ask it to solve for the tropical 0, it automatically gives you this answer. Okay, so it gives us this chamber, and as we can tell, it has 2 inequalities and 1 equality. So that's exactly what tells you that within this, there's some specific hyperplane given by this, within this space, and there's this positive quadrant determined by these conditions. And our trop space became 2-dimensional, as you can see from this picture, which is exactly what is going to be giving us the 1 over epsilon squared divergence. Okay, so if you don't trust me, let's verify this together. So we can look at this trop function, and we can evaluate it on the support of this this condition. Okay, so first of all, this tau2, because of this condition, just becomes a sum of tau1 and tau3. So this factor doubles here. And similarly, we have minus twice the max on this. So we just copied that. In the second slot, we used to have tau2, but now on the support of this condition, it's just equal to tau1 plus tau3. And then we just copied tau3 from here and tau1 from here. Great. So now what you see is that on the support of further these inequalities, these two inequalities, we see that these two factors in fact dominate over the rest because tau1 and tau3 are positive or equal to 0. So these factors are always dominant. Okay, because they're dominant and they're equal to this, there's a factor of 2 in here. So that in fact, that function is in fact always 0 on this specific chamber. So in other words, what we found is that this part of the integrand, which was just what we've seen above, in this specific chamber, we can drop some of the monomials in the F polynomial. And precisely the terms that we can drop are the second to last one and the last one. Okay, so this corresponds to just taking this F and leaving in S and T coefficients, but dropping the masses. And that's exactly this tropical realization of the intuitive notion that the masses somewhere far away from this, these two masses here, M3 and M4, where the masses somewhere far away from the soft collinear divergence, so they should not matter. And this is a tropical realization of this fact. Awesome. So we found that our integrand in this infrared region can be approximated by this function. And in fact, just as before, we've identified the shrinking of the subdiagrams as the like an asymmetry that we see in certain directions. We can go through a similar exercise in here as well. Okay, so the symmetry is going to is spelled out here. So first, let's look at the lambda scaling. So as you can tell, alpha 1 and alpha 3 scale with a single power of lambda, and alpha 2 scales with 2 powers of lambda. So if you apply it in the numerator, it scales like lambda to the 4. And likewise, these two factors scale like lambda squared all squared. So that means that the overall lambda scaling is a symmetry of this factor. Okay, and similarly, you can see that if we additionally rescale alpha 1 with some rho and alpha 3 with some rho inverse, then that rho simply drops out after you do this rescaling, so it's also a symmetry. Okay, so what we found, that you can see that to be consistent with going in this single tropical 0 direction, what you need is that this lambda goes to infinity and rho can be anything. Okay, so that's of course what we intuitively would have expected. Well, the lambda part is what we would have intuitively expected from just being an infrared divergence, because it tells us that these three edges go to infinity, so they rescale to be very, very long, which is a signal of infrared. Okay, and in addition to actually realize the soft collinear divergence, it turns out you also need the scaling in which this leg scales as rho and this scales as rho inverse. So they do this kind of thing. Okay, so actually this specific example was analyzed recently by Akshay, and what you can check is that the coefficient of the divergence that you get from just modeling out by the symmetry and doing the procedure that we've seen above gives us 1 over epsilon squared as expected times some coefficient, which is the correct one. Okay, and in fact, that is a very first example of a classification scheme that we propose for soft collinear divergences, which are based on the so-called COMs. Okay, it's called a COM because it has a single spine here, and it has some teeth sticking out. Okay, so this is an example of a COM that covers L loops here, and it corresponds to some common soft collinear divergence for all the legs, all the loop momenta within these legs. Okay, so let me just briefly tell you what the scaling is supposed to be, just to have some intuition for it. First of all, there's some overall scale, which I called here capital lambda. And this capital lambda, it goes to infinity. So that's precisely the signal of the infrared divergence, because these legs become very long. And also for each subcom, so each, I call the teeth here with the betas and the spine with the alphas. So for each of them, we need this equality, which sort of mimics what we've seen above for a single box example, that this needs to actually scale faster than the adjacent teeth. Okay, and then you can show that, you can prove that this actually, that kind of com leads to precisely a log to the power 2L divergence, where L was the number of loops that it covers. Or equivalently, it also leads to, in DIMREG, to 1 over epsilon to the 2L soft collinear divergence. Awesome. So now what we can do is we can move to combinatorics. And the combinatorics is based on the following compatibility rules for how you can fit different comms into each other, okay? So here's one example. What I mean by this is that we've learned how to do a single comm looking like this. So that's a single soft collinear divergence associated to sort of this line. What you can also do is you can ask how many of them can fit together to analyze properly the divergences. Okay? So first of all, what we have is, let's say we have this 2com. So it's the one that gives us the soft collinear in this region. It's sort of naturally compatible with something far away. So that's not surprising. The red one with the green one are compatible. But then you have to be slightly more careful because, for example, this 2com here, because it gives us some soft, collinear limit here, it actually allows for the blue one to exist further. Okay, so then you can analyze these kind of rules in which different comms factor into each other and allow the existence of the other ones. And we have some diagrammatic rules that are basically exemplified already by this example and the one that will follow later. And just to make sure that we propose this sort of classification schemes for at least the leading infrared divergences, just to make sure that we've covered everything. The cross-check that we've made is we've looked at the log of the n equals 4-point MHV amplitude. Okay, so the way that it looks like is that what you do here is you compute the log of the full MHV amplitude at 4 point, and then you can expand it in terms of the coupling constant, G. So the leading order, this is just equal to the 1 loop contribution. The subleading order is a combination of the 2 loop contribution and 1 loop squared with some coefficients. And likewise, the next order is a combination of 3 loop, 2 times 1 loop, and 1 loop cubed. Okay, so the magic property of this specific combination is that basically most of the naive infrared divergences are supposed to cancel out, and only the measly log squared infrared divergence survives. So that is a great cross-check for our formalism, because, you know, sort of here, say deep in the expansion, there's supposed to be a lot of cancellations that actually probe if we've understood properly the infrared singularities of our amplitudes. And in fact, the most complicated one that we went to is tracking these sort of 3 loop contributions, which include 4 tennis court diagrams and 2 3 loop ladders that you need to check in order to be able to predict that all the divergences cancel out, or rather to cross-check this. Okay, so for example, let me just give you very quickly an example. I think I'm supposed to finish soon, so let me just very quickly give an example of this tennis court diagram that actually contributes to this n equals 4 amplitude. It's not the tennis court itself, it's the one with a numerator. So what you have to do is you have to do this tenfold, well, you have this 10 Schwinger parameter integral. And then you have some U and F polynomials that I'm not going to spell out because they're slightly too long. And what we also found is that there's some nice rules for coming up with numerators for associated to Schwinger parameter numerators associated to loop integral numerators, which are also given in terms of some combinatorics of spanning diagrams within our tennis court. Okay, so we have this integral, and basically we can take this factor and define the trap function associated to it and study all the cones and the ways that they fit together. And what we found is that the leading divergence is actually dictated by the following combination of soft collinear limits, in which we found that there's 10 different regions in the integration domains. Each of them correspond to some specific limit in which the edges in our diagrams have to shrink and contract, rather expand, to see a divergence. And it's diagrammatically summarized by these diagrams. So you can tell, for example, here, there's one cone like that, another soft collinear, and this one. And you can go on. There's some very interesting combinatorics associated to actually how you find those regions. And ultimately, once you sum and look at the leading divergence, you get some number. In this case, turns out to be 16/9, which is, of course, a known answer for this diagram. And then what you can check is that after you do this analysis for every single term in this expansion, you put everything together, you indeed do find that all the singularities cancel out, which tells us that we have correctly found all the infrared divergences of the specific classes of diagrams. Let me, towards the end, let me just, as an aside, let me mention that we found an example of a power law or quadratic infrared divergence, which is something that I was quite surprised that such a thing exists, but maybe someone can tell me in the audience that they've been seen before. And the way it looks like is that you can look at this tennis court diagram, but without any numerator. So the one with the numerator only had log divergences, which resum to this factor. The one with putting no numerator turns out to have power law infrared divergences, which essentially come from the region, if you call this leg L1, L2, L3, in which these the momenta become collinear with P2. And this is, you can actually see this a posteriori in the loop momentum space and see how this actually happens. But in our formalism, it was extremely simple to find such an example because it can be easily diagnosed by the fact that there exists some region in which trap function is positive somewhere in the integration domain. And as you remember, this was supposed to signal to us quadratic divergence or worse. Okay, so in the final 1 minute, let me just very briefly summarize basically 3 takeaway points that I hope you've learned today. The first one is that we've seen that the tropical geometry is really a realization of the idea of separation of scales when applied to a wordline formulation of Feynman integrals. Secondly, we've defined this trap function and looked at specific directions in the integration domains characterized by the fact that the trap is equal to 0 in those directions. And we propose that these determine exactly the directions in which the Feynman integral has some UV or infrared divergence. And finally, we proposed a classification scheme for soft collinear divergences, which are governed by these cones. Okay, so with that, I'm done, and let me thank you for your attention.
Hey, thank you for the beautiful talk. Questions? I see Enrico.
Enrico.
Hey, Sebastian, thanks for this great talk. Do I understand you correctly that, so for this 3-loop example you analyzed, did you only check the cancellation of the leading 1/ε⁶, or did you then take the rest and then check the leading singularity, the leading IR divergence of the rest once you've canceled the 1/ε⁶? Similarly, for your one loop example that you analyzed, I mean, the one loop guy has also like a 1/epsilon pole where you can pinch, one of the legs, and you only have a two mass triangle left, and then you can analyze the leading singularity of that.
We've only analyzed so far the the cancellation at the leading order. So this, in this diagrammatic language, what this corresponds to is fitting as many comms as possible in the diagram. The subleading ones would be the directions associated to fitting fewer comms together, and we're working on that as well. Does it answer your question?
Yeah, I guess
so I should say that the general picture is that there's this tropical zero space, which in this case would be 6-dimensional because there's overall 1/epsilon to the 6. And then within that, you would also find some sub-regions which are of higher codimension, which would correspond to these subleading factors as well. So what we're working on right now is how to correctly determine how they fit together and how to subtract the leading one and then look at the subleading ones and so on. This was just as a cross-check of the fact that we've correctly understood the sort of these compatibility rules between different subcollinear regions.
Thanks.
Thank you. Piotr?
Piotr has a question.
Yeah, sorry, my connection is a bit jumpy. About the, yeah, never mind, it's not working.
Awesome. Any other questions?
Sebastian,
sure.
Can I ask you about the analogy with string integrals?
Yeah, sure.
So if you write down the string amplitude, you can also tropicalize the integrand and figure out the combinatorics of the alpha prime to 0 limit. Another thing you can do in the string amplitude case is you can recover the world sheet, and by asking what integrands would make the string amplitude converge.
Mm-hmm.
Is there such a thing for a Feynman integral in this parameterization?
To answer your first question, the difference to worldsheet in sort of the way that you might be thinking about it in your recent papers is that on the worldsheet, there's sort of, at infinity in every direction there's a log divergence. This is what you regulate, and this is what gives you the overall 1/alpha prime to the dimension of the space. On the actual worldsheet, it's going to be n-3. And this, in our language, what it would correspond to is that the tropical zero spans the full space. So the difference on the level of Feynman integrals is that there's only specific directions in which such a thing happens, not the full space. And moreover, those directions do not even have to be maximal dimensional. They could be some lower codimension, and then you have to see exactly how they fit together in your integration domain.
Yeah, I'm wondering whether there's actually a space, as in a variety that is like M0n, but for when you write down a Stringer parameterized Feynman integral, does it come with a space like M0n?
Yeah, in a sense, it comes with a space which you can call a moduli space of Riemannian metrics on a diagram. So it's just literally what I described, which is the space. Yeah, it's just space of metrics on a diagram, right? So it's described by the lengths of each edge modulo the overall rescaling invariance. So you might be asking, is the tropical compactification the compactification that is somehow unique or physically?
Well, in the stringy canonical form case, there are two things that give the same combinatorics. One is you would call the kinematic space, and the other one is the worldsheet space. And one of them is flat, and one of them is a variety. And I'm just wondering whether you, I mean, from your talk, I saw that you're looking mostly at the combinatorics, or sort of the polytope side. I'm just wondering whether there's also analysis of the curvy side from just from tropicalizing the integrand.
Yes, absolutely. Let me actually mention something which is closer into the spirit that you might be used to, which is that we've studied the Feynman integrals in this language, in which we have u, f, and something like this, and then we regulate the things with the overall epsilon here. Okay, and the analog of the your alpha prime is that the reason why kinematic space in quotation marks doesn't exist in this case, when I say kinematic space, I mean sort of basically space of these epsilon invariants, so very loosely, is that we only have one. Okay, so what you would actually like to do is you would like to introduce at least as many regulators as the number of integrations. And it turns out such a thing exists, and it's given basically by multiplying everyone to its own epsilon, like this. In this way, you have the same number of epsilon as the number of actually one too many than the number of integrations. And this is exactly this setup is called analytic regularization, and this is exactly something that we're looking into, in which we can map how this integral behaves as a behavior in some kind of epsilon space, the analog of your kinematic space in the.
But here the polynomials that are being raised to epsilon powers are kind of boring. You're just taking a monomial in whose exponents are epsilon. You're not putting an interesting polynomial to epsilon. Well, in the string amplitude case, you're putting an interesting polynomial to a power.
Just to be precise, these numerators are also modified with these epsilons.
Oh, okay.
So everyone, there's some interesting thing raised to a power. In fact, that is what gives you some interesting combinatorics in the epsilon space. The difference, of course, to stringy canonical forms is that these are no longer D-log forms. Right, so it's not epsilon to the -1, is epsilon, and we're strictly interested in the limit as epsilon, these regulators go to 0. So that's the source of the difference. But what you can show is that in the specific directions in which the integral does look like it's d-log of something with a regulator, this is exactly in which you see some hints of positive geometry-like objects, and that's what I was hinting at.
So in this version, this analytic regularization, do you also have scattering equations that computes the limit as well? We don't know that. We don't know that. Certainly, there doesn't exist a global notion. It would have to be so. There's some overall space, and within that space, there's some specific directions, and these directions would be these tropical 0 directions, and within those subspaces, this is where your integral looks sort of like the stringy version of it. Stringy canonical form. I don't mean to imply it looks like string theory.
Yeah, if I could just amplify. Go ahead, Sean. Yeah.
I mean, very, very closely related. The fact that when you go to this lower dimensional space with chop equals 0, that the leading order is given by the volume of the dual polytope, that is not it's certainly not a coincidence that this agrees with the full dimensional case where for stringy canonical form that the leading order is the volume, right?
It's exactly the same derivation, if you will.
I see.
But
I mean, is there like a version that give you the most general analyze, which imply both? Because here there's also something special that you only have one epsilon, and
so we also analyze this analytic regularization version in which the things are even closer to your story. There is an analog of this epsilon space in which you can find this curvy to flat realization, but once again only the tropical 0 subspaces.
If I could just add something, I mean, one of the, in the discussion, we've already talked about the fact that the 0th order difference is that we don't get divergences in the entire space, but they're localized to the subspaces where we have trop equals 0. So we have this kind of the simpler story that we're used to is realized on each one of these trop equals 0 spaces. Something that's kind of fascinating is that these F polynomials and the U polynomials, the combinatorics associated with them and their Newton polytopes do something interesting in a way that has nothing to do with the number of space-time dimensions, nothing to do with the sort of details of any of that. And it's these objects that have these sort of perfect factorization properties that reflect the shrinking of graphs and factorization and all of that, in a way that doesn't know if you're in 2 dimensions or 300 dimensions, or is not directly related to the divergences of the actual loop integral. So that's kind of fascinating that these polytopes exist. They do this perfect factor. I mean, the Newton polynomials for U and F are the perfect analog of the isosahedron and their generalizations for long distance factorization. It's just wonderful that they perfectly reflect the shrinking of subgraphs in a very precise way. But somehow, for the physical problem, and even sort of more manifestly in analytic regularization, we're not seeing all of the facets of this guy. Once you decide what your number of space-time dimensions is and so on, you're only seeing some set of the facets of this guy contribute to the answer. And it's a little bit like in the story of the isosahedron when we talk about the amplitudes in different orderings. You don't see all of the facets of the isosahedron. You only see the one with the poles that are compatible with the orderings that you talk about. And then there is a simple way of getting the sort of full answer from getting the answer you want from the full answer by sort of throwing out the terms that are not associated with that ordering. It kind of looks like, well, this is something that we're looking at now, that if you look at the canonical forms for the F polynomials, for the F Newton polytopes, and then you throw out the terms that don't actually correspond to divergences in the number of space-time dimensions you're in, that gives you the sort of right answer for the leading divergences in analytic regularization. But anyway, yeah, it would be wonderful if there was a very sort of a clean picture for talking. I mean, I think for the leading divergences, there's a very clean picture, and that's what Sebastian was beautifully describing in the talk. But sort of going systematically from there to the sub-leading divergences and the sub-sub-leading divergences, all having to do with the fact that the divergences are, to begin with, living on these lower dimensional trop equals 0 spaces. I think that's the sort of central novelty relative to the other things that we've talked about, which of course is associated with the fact that we're not dealing with D-log forms from the get-go, exactly as Sebastian explained.
I see.